Hi, Algebra 2 students. I am here to work out the quiz review for you live and in person so that you can actually see where these answers came from. And in a couple of cases, I want to point out something that on the key I gave you, I might have written a little differently because that was not actually a key that I came up with. So let's go ahead and look at this, starting with problem number 1. It says the mean life of a tire is, and that should be 30,000 kilometers. The standard deviation is 2,000 kilometers. Draw a picture to use as a reference. Now, here's the first thing I would say that I probably would have done it a little differently, is I would have called this mu. We're not using X bar for this because we're not saying this is a sample of tires. This is assumed to be the data that is about all tires. So the mean life of a tire based on the life of all tires ever is mu. The mean life, if I just said we took a sample of 100 tires, then our mean of that sample we would call X bar. But we're not really getting into that. So that's my mu, and this is my sigma. Draw a picture to use as a reference. All right, so we're going to draw the lines and then use the empirical rule. The empirical rule is the one that has these percentages, which we should know. Okay, so you need to know these percentages. They are always the same for the empirical rule. This is 2.35%, and this is 0.15%. This is 13.5, 2.35%, and 0.15%. Okay, so 68% of all tires, I'm sorry, I didn't finish the standard deviations. So this is my mu, this is 30,000. And then I'm going to add 2,000 and add 2,000 again and add 2,000 again. And going the other way, subtract 2,000. All right, so 68% of all tires, that's the middle two sections here. So basically within one standard deviation of the mean, which is 30,000 here. So that means from 28,000 to 32,000. Okay, 95% of all tires, that's within two standard deviations of the mean. So from here, 2 to the left, to here, which is 2 to the right. So between 26,000 and 34,000. And these are standards. These are things that are always true on the empirical rule, or with the empirical rule. What percent of the tires will have a life that exceeds 26,000? So that means from here up is what percent? To me, from here up, it's easier, instead of adding those all together, which I could do, is just to know that from here down is 2.5%. These two together always equal 2.5. So from here down is 2.5%. If I take, since they asked in percents, if I take 100% and take away 2.5, I get 97.5%. So that's what I'm going to put here. If a company purchased 2,000 tires, how many tires would you expect to last more than 28,000 miles? Okay, more than 28,000 is from here to the right. Well, from here to the right, from the mean to the right is 50%. So from here to the right is this 50% plus another 34%. So that's 84%. So I'm being asked what 84% of 2,000 is, which means 0.84 times 2,000, which I will go to my calculator with and type 0.84 times 2,000 and get 1,680. And that's what I would expect. That's how many tires I would expect to last more than 28,000 miles. Moving on, a bottle of fruit punch contains at least 473 milliliters. The machine that fills the bottles is set so that the mean volume is 477. So that's my mu. This is 477. The volumes are in the bottles are normally distributed. Okay, so let's go ahead and complete these lines. It didn't really give me much at first, so let's see what they're going to ask me. And I want to go ahead and put my percentages in here. Okay, so I went ahead and filled those in real quick. Let me remind you that this particular picture is not really the best because it looks like it touches here, like it hits the horizontal axis. It doesn't. Remember, it keeps going out forever. So this does have some space under the curve over here, and it has more space under here under the curve. Just keep that in mind. It's a visual issue, really. So what % of the bottles are underfilled? Now remember, hang on one second. What % of the bottles are underfilled if the standard deviation is 2 milliliters? So basically, we're going to have to do this a couple of times. We're going to have to look at this, and then we're going to have to go back and change it. Standard deviation being 2 milliliters means this would be 479, 481, 483, 475, 473, and 471. Okay. Okay, so I just actually paused and looked at this a second because I think that the wording of this problem makes it a little bit hard to understand what's being asked. It says, what % of the bottles are underfilled if the standard deviation is 2 milliliters? So we go back up here and say a bottle of fruit punch contains at least 473 milliliters. And you're looking, you're like, well, what about these? Well, that's what it's asking about. Really, what this should say is a bottle of fruit punch is supposed to contain at least 473 milliliters. So in other words, that's the standard. We're supposed to have our bottles have at least 473 milliliters in them. And we're asking what % don't, what % are less than that. So that would be these two sections here. And together these add up to 2.5%. The next question is asking, or the next part is asking the same question basically, but there's a different standard deviation. So we have to go back and relabel these. So let me go ahead and pause and do that. Okay, so now the numbers in blue are filled in according to part B. I went back and I used a standard deviation of 4. So 477 plus 4 plus 4 plus 4. Going to the left was minus 4, minus 4, minus 4. So what % of the bottles are underfilled if they're supposed to contain at least 473, which is right here? The % that's underfilled would be the ones that are to the left of that. So together these two are 2.5% and this is 13.5%. So that together makes 16%. All right, moving on. The speeds of cars on the highway have a mean of 95 kilometers an hour with a standard deviation of 5. Draw a picture first. Okay, so I went ahead and filled in. The mean was 95, standard deviation was 5, so I added 5 going right and subtracted 5 going left. I haven't filled in my percentages, but let's see how that works. What percentage of cars average less than 85? So that means from here down. Well, this is the 34% area. This is 13.5. So this is the 2.35%, and this is the 0.15%. And we've said a couple of times here that those two together are 2.5%. All right. Now, if a police car stopped cars that were going more than 105, so that's the same thing on the other side, those last two sections. Okay, so remember this is 2.35% and this is 0.15, and together that makes 2.5%. How many cars would they stop if there were 8,000 cars on the highway? So we're talking about what's 2.5% of 8,000. So we're going to go 0.025 times 8,000. And that gives me 200 cars. Okay, moving right along. Number 4. The mean life of a battery is 50 hours with a standard deviation of 6 hours. The manufacturer advertises that they will replace all batteries that last less than 38 hours. If 50,000 batteries were produced, how many would you expect to replace? So the mean is 50. I'm liking this blue, so I'm going to stick with it. Standard deviation is 6. So 56, 62, 68, 44, 38, and 32. Okay, they will replace all batteries that last less than 38. So that means all that are over here. This is the 2.35% area, and this is the 0.15% area. And we've talked about how these two add up to 2.5 several times now. So those two sections, that's 2.5% of the batteries. So if there are 50,000 and we expect 2.5% of those 50,000 to be replaced because they have lasted less than 38 hours, we're going to do in the calculator 0.025 times 50,000. And that gives me 1,250. All right. On a recent math test, the mean score was 75 and the standard deviation was 5. Okay. I'll let you skip my drawing. Okay, so you notice it says on this one, draw a picture first. And I did my picture with the standard deviations in place. And then I looked at what they're talking about, and they're talking about Mike making a 93. All right, so we have a problem here, and that is that 93 is not one of these numbers. 93 is over here somewhere. And again, remember that just because it looks like there's no curve there, the curve really looks more like this. There is space over there. Okay, so what percentage of students score better than Mike? We would expect it to be very few students, okay, because only 0.15% are going to be higher than this. 0.15% are in this category from 90 up. So we would expect a very small percentage of students to score better than Mike, but here's the deal. We can't find an exact answer using the empirical rule. The empirical rule means those standard percents that are always true when we have exactly spaced out standard deviations. Okay, so that means it's time to use a z-score table. Now, let's do this one both ways. We can do it as a z-score table, or we can do it on the calculator. I want to do it both ways because your quiz might ask you to do something a particular way that really does require doing it that way for you to understand it or to get the right answer. So let's look at it both ways. We'll start with a z-score table. First, we have to find the z-score of 93. So remember, we do mu minus, no, I'm sorry, we don't. We start with our x value minus mu divided by the standard deviation. So our x here is whatever number we're working with. So this is 93 minus mu is 75, and the standard deviation here was 5. So that's going to be 18/5, and 18/5 is 3.6, I believe. Okay, so there's my z-scores, 3.6. Let me just double check myself. For some reason I'm feeling insecure, but yes. So now I'm going to go to the z-score table and look for 3.6. All right, so I have my z-score table and I'm looking for 3.6. So I need to look at positive 3 and then go over to 0.6. Here's positive 3 right down at the bottom. And I go over to 0.6 and I get 0.9998. So that's the same as 99.98%. 99.98% of people made a higher score than him when he got a 93 and the class average was a 75. That doesn't make sense, right? Don't forget, the reason why is that's actually less than. That tells me what percent made less than he did. Okay, so the percentage of students that made less, we can subtract from 1 or change to a percent and subtract from 100. In other words, I can say 1 minus 0.9998 and do that and get, that says 2 times 10 to the negative 4th. What that means is 1, 2, 3, 4. That's what that means. Or we could also do it as a percent. We could say that's 100% minus 99.98%, which is, move the decimal twice, it's the same thing, 0.02%. They asked me for my answer as a percentage. Okay, so if I got this answer, I would then move the decimal twice and change it to this answer. And that is my answer. 0.02% of students scored better than Mike. Okay, so now let's do the exact same problem, but not with the z-score and table, with the calculator instead. With the calculator, I need to think about boundaries of the shaded area. So in other words, my shaded area is between 93 on the left and really infinity on the right. Okay, really it's pretty much infinite. But we can't type in infinity in the calculator, so we have to just pick a number that's really, really big and type that in instead. Okay, so now let's remember what goes in the calculator. When I go to normal CDF, remember to use CDF, not PDF. I have my lower boundary, which means the left side, my upper boundary, which means the right side, and then mu, and then sigma. All right, so my lower boundary is 93. My upper boundary is just going to be a really big number. So let's go ahead and do that. I did second vars to get here. That's the little distra for distribution. 2. So we just said the left boundary is 93, comma, and just big number. So I'm just pressing in 9,999. That's my right boundary. And then mu was 75 and sigma was 5. Okay, and I get 1.59. Don't miss the E. Okay, if you typed in 1.59 for your answer here, it would be wrong. All right, so make sure you catch that E. And I'm trying to grab a blank piece of paper. This means 1.59 times 10 to the negative 4th. So 1, 2, 3, and then 4. It was after the 1, so there's 4 places here. In other words, this is 1, 2, 3, 4. Same idea. Okay, that rounds to the same number we got before, and that's 0.02%. All right, so we got the exact same answer either way. And usually it would probably say round to the 100th of a percent, or round the percent to 2 decimal places, or something like that. All right, next, number 6. A grading scale is set up for 1,000 students' test scores. It is assumed that the scores are normally distributed with a mean score of 75 and a standard deviation of 15. Draw the picture first. So 75, add 15, add 15. Woo, we're getting way up there, 120. Subtract 15, subtract 15, subtract 15. How many students will have scores between 50 and 80? 50 and 80 are not numbers that are on this x-axis. They're not right at 1 standard deviation or 2 standard deviations. So that means I can't use the empirical rule. It means I have to use the z-score table or the calculator. I'm going with calculator this time. So here's 50. And here's 80. And we want to know how many students are between here. So first we're going to have to figure out what percent of students is between there, and then deal with that at 1,000. Okay, so my left boundary here is 50 and my right boundary is 80. So when I do the normal CDF, I'm going to do 50 first and then 80. Then my mean is 75 and my standard deviation is 15. So in the calculator, second bars, second bars, I pressed second twice by accident, hit 2, left 50, right 80. And then the mean is 75 and the standard deviation is 15. And that's 0.58 0.527, which is the same as saying 58.27%. So 0.5827. So if I want to know how many people out of 1,000 have those scores between 50 and 80, then I can go ahead and leave it as a decimal and multiply this decimal times 1,000. Because if I changed it to a percent and I got 58%, I'd still have to change it back to a decimal to use it. So the answer is 582.76. So let's go ahead and round that to 583 students. Next, we have if 70 is the lowest passing score, how many students are expected to pass? So let's see if I can grab a different color here. Let's see if this shows up. There we go. So here's 70. And passing would be above that. So that means everybody over here. Okay, so now just looking at the purple, lavender, what have you, my left boundary is going to be 70 and my right boundary is going to be super big number, like infinity. But we're not going to actually type in infinity because that's not a number. We can't. So second, vars 2. We have the same mean and the same standard deviation. So it's really the only difference that changes here are my left boundary and my right boundary. So my left boundary is 70. My right boundary, just really big number. I just typed a bunch of 9s. If I'm looking for a right infinity, I type a bunch of positive 9s. Left infinity, I type a bunch of negative 9s. Or I type a negative and then 99999. You could type 10,000 instead. You don't have to use 9s. I find it just the easiest thing. You could use 1s. You know, 1,100,000, 111,000 is still a really big number. But that's just the easiest thing to me to type real quick. And then 75 and then 15. And I get 0.6305. So that means 63% of the students. Now they want me to take that 63% and find out how many actual students. So instead of changing it to 63% and then having to change it back to a decimal, I'm going to leave it like this and multiply it times 1,000 students. And it turns out that 630.55, so let's round it up and say 631 students passed. All right, on number 7, it says the monthly income of 5,000 workers at the Microsoft plant are distributed normally. Suppose the mean monthly income is $12.50 and the standard deviation is $2.50. So it goes up like this and down like this and so on. And I'm not finishing it because I already drew them for you. And I just want to look at the fact that we've got 3 different questions here. And so I decided to give you 3 different drawings so you could see what's going on. First one is how many workers earn more than $14.50 a month. Second is how many workers earn less than $700 a month. And then finally, what percentage of the workers are between here and here. Another thing we have to notice here is the difference between asking how many and asking what percentage. Remember that when we put it in the calculator, we're going to figure out the percentage or the decimal out of 1. So if we want to know how many, we're going to have to take that decimal and multiply it times the total number of workers. All right, so let's look at the picture for A. How many workers earn more than $14.50? That's what this looks like. B was how many workers earn less than $700. And C was what percentage are between here and here, between $6.50 and $15.50. So this one, my left boundary, here's the right boundary. My boundaries are on the left, $14.50, and on the right, infinity. So again, we can't type in infinity, so we just type in a really big number. So this is what we're going to put in here. And I need to put more than, if I put like 3 9s, that would not be bigger than $14.50. 9,000 is bigger than $14.50. I might even put an extra one just to make it really a lot bigger than the mean. And then that number. The mean is $12.50 and the standard deviation is $2.50. Okay, next one. Sorry I wrote so big. Kind of squeezed you part B. The left-hand side here, this is like negative infinity. So we're talking a really big number in the negative direction. So say like negative 9,999. Then the right boundary is 700, and then 1250 and 250. And then down here is a little bit nicer because we do have two boundaries. 650 on the left, 1550 on the right, and then our mean, and then our standard deviation. Sorry, you can't see that very well. So these are what you're typing in for each one. Okay, when we type in A, we get 0.2118. So that means 21% of workers make more than 1450. But we weren't asked for what percent, we were asked for how many. So if this is the percent of workers that make more than 1450, I'm going to take that number, it's already in decimal form, so I'm going to leave it there, and multiply times the total number of workers. And my answer is about 1,059. So this is 1,059 workers. Then for part B, here's what we're going to type in. So, big negative number. Notice I'm typing even more nines in there. I want to make sure it's very far away from the mean. And I get 0.0139. 0.0139. It makes sense that it would be a smaller number. Remember, the whole area under the curve is 1. Okay? And 68% of that, 0.68, is right here around the mean. So this is pretty far over. So it makes sense that it would be a pretty small number. So this is the same as 1.39%. All right? So if I want to know how many workers, I would take my 1.39% and change it back to a decimal, which it already is. So let's leave it like that and multiply times 5,000 and get 69.51, so about 70 workers. About 70 workers earn less than $700 per month. And then finally, for what percent earn between, that was these numbers right down here. So let me type those in. Typing all kinds of wrong things. So I'm trying to clear my screen and I hit the wrong button. And I get 0.8767, or about 87.67%. And this one I was actually asked what was the percent. So about 87.67%. Let's go to the nearest tenth and call it about 87.7%. If I was taking this as an online quiz, I would definitely look and see what does it want me to round to. All right, next we are looking at actual, definitely have to use the formula, or excuse me, I have to use the table problems. I've been using mu for this because it's technically what we're looking at is the whole population. So x bar mu, same thing, they both mean the mean. Number 8. A patient recently diagnosed with Alzheimer's takes a cognitive abilities test and scores a 45. The mean on this test is 52. So that's this. The standard deviation is 5. What percentage of students scored below, and I would say patients, scored below a 45? So the patient scored a 45, that becomes my x. So using this formula, my z-score is going to be 45 minus 52 all divided by 5. That's negative 7 divided by 5, which is negative 1.4. So there's my z-score. And if I want to know what percent of patients scored below that, that means to the left of, so that's good because remember, z-score table only tells us the to the left than. Okay, so we're looking at, here's mu, here's a z-score of negative 1.4. We want to know that amount, And that's exactly what the table tells us. This is not the clearest table. Sorry about that. Let's see if I can find you a better one. Negative 1.4. Negative 1.4 is going to be 0.0808. All right. So 0.0808 is the probability. And honestly, this is asking about it as probability. So the way this is phrased, I would probably put that. But it also says what percent. So as a percent, that's 8.08%. This was not wrong. I just moved it up there. Okay, so this notation actually means what's the probability of being to the left of x being to the left of. That's not the best notation either. Really, it should say probability of x is less than 45. That's what it really should say. Either way, there's your answer. Number 9, a 5th grader takes a standardized achievement test where the mean, mu, is 125 and the standard deviation is 15 and scores a 148. So that's our x. X is 148. What percent of 5th graders scored above a 148? So mu is here in the middle, 125. Here's the 148. We're asking for the area to the right of that. Remember, the table gives us the area to the left, so we're going to have to subtract from 1. Okay, because the entire area under the table is 1. So z-score, first off, I have to use my formula from up here again. So x minus mu divided by standard deviation, or sigma. So my z-score is 148 minus 125 divided by 15. So I'm going to go ahead and go to the calculator for that. 148 minus 125 divided by 15 is 1.53 repeating, so let's just call it 1.5. Then I go on the table to positive 1.5. Let's go ahead and write that down. Positive 1.5. Let's see if I can read this table. And I believe it's 0.9332. Okay, so did 93.32% score above that? No. 0.9332, by my other color, is over here. We want to know over here. So we're going to do 1 minus that. Let's go ahead and say 1 minus 0.9332. That gives us 0.0668. 0.0668. So I would say the probability of x being higher than 148 is 0.0668. It says what percent though, so I'm going to say my answer is 6.668, or let's say 6.7%. Number 10, Pat and Chris both took a spatial abilities test with a mean of 80 and standard deviation of 8. Pat scores a 76 and Chris scores a 94. What percent of students scored between them? Okay, so with z-scores, I honestly would probably cheat this one a little bit, unless, let me get there. Let's talk about this. The z-score for Pat scored a 76. So 76 minus the mean, which is 80, all divided by the standard deviation, which is 8. So that's -4/8, which is -0.5. So that's Pat's z-score. Chris scored a 94. So 94 minus 80, all divided by 8, that's 14/8, which let's go ahead and change that to a decimal. And we get 1.75. Let's round it up to 1.8 because our z-score table only goes to the 10th place. All right, so if we were strictly using z-scores, here's what I would do. I would find the answer for the z-score of -0.5. That would give me this value over here. I would find the answer for the z-score of 1.8, and this would give me this value. And if I wanted to know between them, I would take the bigger one and subtract out the smaller one, which basically takes this part off and gives me the part between them. All right, so if I had to use a table, I would do it that way. If I'm allowed to use my calculator, that's going to be a little bit easier here, honestly, because of the between. But it really depends. The way this is phrased right now, I would go ahead and use my calculator, I think. I don't know. Yeah, I probably would. But I don't know. I probably would check it too. I probably do it both ways. Because the concern is, what if you're supposed to use the table? And this kind of implies we're supposed to use the table because we were asked for z-scores. But it doesn't specifically say use the table. Let's go ahead and use the table first and then check it with the calculator, because you might get a slightly different answer. You almost guaranteed, honestly, will get a slightly different answer. The question is how much different. Okay, so z-score for Pat is -0.5, z-score for Chris is 1.8. Okay, so let's go ahead and look at those. For Pat is -0.5, -0.5 is 0.3085. Okay. So here's Pat, and 0.3085 is over here from Pat. Then Chris's z-score was 1.8. 1.8 is 0.9641. So here's Chris, and from here to the left is 0.9641. So in other words, 96% of people scored below Chris, 30% of people scored below Pat. So if I want to know how many people scored between them, I'm going to take this whole section and subtract out this part. So in other words, 0.9641 minus 0.3085. 0.9641 minus 0.3085 gives me 0.6556. So 65.56% of people scored between them. Was it asked as a percent? Yes. So 65 point, and I said 56, let's go ahead and round it. Now let's see what happens if we had done this as in the calculator. In the calculator, we don't need z-scores. There's actually no place to put z-scores. So in the calculator, we're doing normal, and you can use the calculator, even if it did say you have to use the z-score table on this one, you can use the calculator to check yourself and make sure it's close to the same answer. We're looking for between 76 and 94. That's what we're trying to find here, because remember, Pat had a 76 and Chris had a 94. So lower boundary is 76, upper boundary is 94, the mean is 80, and the standard deviation is 8. Everything we did with z-score is irrelevant if we're using the calculator. So we get 0.651, so 65.1%. So we would get a slightly different answer. But it's close enough that you can tell, if you were unsure about this answer, that yes, we did the right thing. Let's say that you were much more comfortable using one way than the other. Let's say you're much more comfortable using the calculator. And so when you did this, you were like, I'm not sure I did the right thing. Check it on the calculator. Yeah, that looks right. All right, the Welcher Adult Intelligence Test Scale is composed of a number of subtests. On one subtest, the raw scores have a mean of 35 and a standard deviation of 6. Use the information to answer these questions. What's the z-score of a person who scored a 54? That's x minus mu all divided by sigma. Let's say, yeah. So that's 19 divided by 6. And we get 3.16, so let's go ahead and say 3.2. What percent of students scored above a 37? Okay, again, I would look very carefully to see if we are told that we have to use the z-score table here. If not, since I don't even have, that would mean I would have to find this z-score first. If they had asked me about this, I would probably say, okay, I've already got the z-score, let's just go with the z-score. But I don't have the z-score of this for this one, so it's not like I've already started doing it z-score way. So I'm going to use my calculator. Normal CDF above a 37 means 37 is the lower end, and it goes to the right from there, so like really big number. And the mean was 35, and the standard deviation was 6. So that's what gets typed in here. Try to make it as visible as possible for you. .369, or about 36.9%. What percent of students scored between a 37 and a 54? The only difference between 12 and 13 is they gave me an upper boundary. Okay, above a 37 means 37 is the left or lower boundary, and then I made almost like positive infinity for my upper boundary. This means this is my lower and this is my upper, or left and right. Left and right. So basically I'm just putting a 54 here. So let's go ahead and see if I can easily correct that. .3686. So that's 36.9% if I round to the nearest tenths again. That's interesting. Okay. If we look at that, and that's correct. Okay, I know it seems weird, but that's correct because look at these two numbers in the calculator. Yes, there were more people who scored from 37 up for, was it 37? Yeah, from 37 up to infinity. This number is bigger than this number. But 54 is high enough that very, very few people scored above that. So that's why if we're rounding to the tenths place, the number of people who scored from 37 to 54 is almost the same as the number of people who scored from 37 and up to infinity. What percent of students are between a z-score of negative 2.1 and positive 2.1? Okay, they gave me z-scores here, so let's go ahead and use the table. All right, a z-score of negative 2.1, that's negative 2.1 standard deviation, or 2-point standard deviations to the left of 0, and a z-score of 2.1 is 2.1 standard deviations to the right of the mean. Which when I said of 0, the mean has a standard deviation of 0. There's no standard deviations at the mean. All right, so 2.1, negative 2.1 is 0.0179. So 0.0179 people scored from here to the left. Positive 2.1 is 0.9821. So from here to the left is 0.9821. So if I want to know between them, that's basically, I was looking for another color, but let's go between here. That's what I'm looking for. So I'm going to take 0.9821 and I'm going to subtract 0.0179. And I get 0.9642. So between here, wish I hadn't written that there, but between here is 0.9642. How was I asked to answer? What percent? So 0.9642 means 96.4%. And that is it, I believe, for our review. So I hope this helped if there were any questions you had after looking at the key. And I think that you'll probably find the quiz to be pretty straightforward and right along the lines of these same types of questions. And I will be on Zoom or Meet, whichever one we're doing, on Monday. And I got to remember when, because we changed the time a little bit, didn't we? I might have to check back on that with you. Because I think the time we chose, I think we're maybe 3, maybe 4. But Checky class, I will remind you there. Thanks so much.